take a look now at the connection between implicit differentiation and the chain rule. So I've got this equation up here, x squared plus y squared equals 1, which we know is our familiar unit circle. And I mentioned that I can view that as a level curve for this function f of xy equals x squared plus y squared. It's a level curve for that function of two variables. Now, in first semester calculus, you learned how to use implicit differentiation to find dy by dx. We can say this equation implicitly defines y as a function of x, and we can use implicit differentiation to find a formula for dy by dx. Of course, that description that you got didn't refer to this function f because you didn't know that functions of two variables even existed, perhaps, at that point in your math career. Okay. What we're going to do is we're going to use implicit differentiation together with the chain rule for functions of multiple variables. So we're going to get the same formula for dy by dx, but we're going to take a look at its relation to this function f, where that's a level curve for that function. What I want to do is first completely ignore these directions and just do this the first semester calculus way, so that we remember how implicit differentiation works. So I would say, okay, implicitly y is some function of x, so I'm going to take the derivative with respect to x of both sides, x squared plus y squared, and then the derivative with respect to x of 1. And I find it helpful whenever I'm viewing a letter as being some function to just put it in parentheses so that I can see that this is a function composition here. That's y, which is a function of x, being plugged into the squaring function. Okay, so working our way across, we would get 2x plus, now here we're using chain rule, that would be 2y times dy by dx, or I could write y prime here if I wanted to, and that's going to equal 0, because the derivative of a constant is 0. And then, of course, I'd want to solve for this, so I'd subtract over the 2x, so dy by dx would be negative 2x, and I'd divide by the 2y, and then I could cancel the 2's, and we get the opposite of x over y. Of course, with the understanding that if y is 0, that's going to be undefined, and geometrically, very nice to see, that at the points on the unit circle where y is 0, the derivative should be undefined because those would be the 2 points where we have a vertical tangent. Okay, excellent. So I know from this that dy by dx, the formula for the derivative of that implicit curve, is just the opposite of x over y. Okay. But that has nothing to do with the name of f. It doesn't give me a relationship to that original function. So now I'm going to try to combine this with the chain rule. Okay. So usually if I have f of xy, we say that the output would be z. So we're saying our z value, which is constant at 1 because we're restricting ourselves to a level curve, that's a function of x and y. X, of course, is a function of itself. That would just be the identity function, x is x. But we're saying that y is implicitly some function of x. Okay. Now, what's interesting here is that x shows up on more than one level. Okay. So I have to be very, very careful here because I want to avoid referring to derivatives of z with respect to x unless I'm talking about the entire relationship between z and x. So in theory, you might say, well, I could call this the partial of z with respect to x because this is a partial derivative. But this would be the full derivative because z ultimately depends on just one variable. I'm going to completely avoid that, though. Because there are going to be some times where we're going to have multiple variables down here. So saying the partial of z with respect to x would be completely ambiguous. Which part? Do I mean this, the top part, or the bottom part? Anytime I have variables showing up on more than one level like this, I'm going to need to use the name of the function. Okay. So when I'm talking about this derivative, I'm not going to write partial z partial x. If I'm using z's and x's, the rule is I'm combining z with the lowest version of x. So that notation is out. I'm going to instead call this the partial of f with respect to x. So when a variable only occurs on one level, it does not make a difference whether you refer to the derivative by the name of the function or by the output of the function. But when a variable occurs on multiple levels, you want to use the name of the function to say, hey, I'm only talking about the relationship between x and the output at this top level. F has nothing to do with what's going on down here. Okay, so this would be the partial of f with respect to y. Okay, excellent. And then I can say here, this is going to be just dx by dx, which I actually know is 1. And this would be dy by dx. That's the thing that I kind of like to know what it is. Okay. Well, using my chain rule, I'd be able to say that dz by dx. Now there, that's legal. If I'm using the names of the variables, the rule is I'm going from the top value here, connecting it to the lowest occurrence of x, which is down here. So I'm looking at the entire relationship between z and x, not just part of it, but the whole thing, all of the ways in which that variable affects that variable. And that would be a full derivative because we are looking at this being ultimately a function of one variable. X is itself, x implicitly gives me my y value, okay, and then those two give me my z value. So just using the chain rule, partial of z with, the full derivative of z with respect to x is the partial of f with respect to x times 1 plus the partial of f with respect to y times dy by dx. Okay. So I get this nifty equation. Notice we're ultimately trying to describe dy by dx, and my directions were to try to describe it in terms of f. Well, this piece and this piece involve an f. Okay? Just seem to have this extra thing right here, but I know what that is because we are applying this to this level curve. We are not looking at the graph of the entire function, z equals f of x, y. That would be a surface in 3 space. We're looking at this level curve. Along that level curve, z is constant at 1. What's the derivative of a constant? 0. So that is 0. Let's just write that down. dz by dx equals 0 because z is constant on the level curve. So we're not using the chain rule here in order to figure out what dz by dx is, because we know that. The derivative of 1 is 0. Okay? We already knew that. What we're doing is we're using the chain rule to see the relationship between these individual pieces. Because now I have 0 equals the partial of f with respect to x plus the partial of f with respect to y times dy by dx. Now, if I wanted to solve for dy by dx, I can do that. Okay, let me give myself some space. Okay, so I'm going to subtract this over and divide by this. So dy by dx is going to be the opposite of the partial of f with respect to x divided by the partial of f with respect to y. Notice that does exactly what I wanted it to do. That gives me this derivative in terms of f. It's this ratio, well, the opposite of this ratio of the partial derivatives of f with respect to x and y. And now let's go ahead and actually calculate that and see that it agrees with what we got anyway using implicit differentiation. So let's see, if this was f, what's the partial with respect to x? It would be 2x. So on top I have the opposite, just because I have that negative sign, of 2x. What's the partial with respect to y? 2y. That should look very familiar. That's exactly what we got last time. And of course I can cancel those 2's and then I get negative x over y. So I get the exact same formula, but if I stop at this point, I can see the relationship that this derivative has to the function f, where I was working with a level curve for the function f. Very cool. Now, if I were to give you something like this and say, use implicit differentiation to find dy by dx, well, you could do that the 3a way, or you could do that the 3c way. Okay? I probably wouldn't give you a question like this and just say use implicit differentiation. If I were going to give you something like this, I would probably give you directions like this. Use implicit differentiation together with the chain rule to express this in terms of f. Now I might ask you then, and then simplify. So I would be looking for this and this. This would be expressing it in terms of f. This would be simplifying it. Or I could simply ask you to use implicit differentiation in the chain rule to derive the formula for expressing dy by dx in terms of the partials of f. So I do want you to be familiar with this process. I might ask you to derive this formula and just stop there, or I might ask you to derive the formula in a specific example and then simplify it as we did here.